Hello and welcome. We're pleased to have you join us today for this first webinar in our fatigue testing of metal series. We'll be hearing from Dr. Erik Schwarzkopf, Senior R&D Engineer and Staff Scientist here at MTS Systems. Dr. Schwarzkopf brings more than 35 years of experience in materials testing, metallurgy, and systems engineering, and is looking forward to sharing some of his fatigue testing knowledge with you today. Before we get started, here are a few housekeeping items to keep in mind. First, we're recording this webinar and we'll be sharing the recording online at a later date. You'll receive an email notification once the webinar is posted. Second, we have quite a few folks on the webinar this morning, well, today more, and we will address questions at the end of the webinar. You may submit questions anytime through the chat function, and we will address as many as time permits after Dr. Schwarzkopf's presentation. So, without further ado, I'd like to turn the webinar over to Dr. Schwarzkopf to discuss the fatigue testing of metals.
Thanks, Andrea. This is Erik Schwarzkopf, and I ran my first high cycle fatigue test on MTS equipment about 42 years ago. I was in the university at that point in time, and I was doing high cycle fatigue for my master's thesis. So let's continue on here. We really can't talk about fatigue unless we talk about mechanical design. And there we go. Jumped ahead too far. So mechanical design, and for a long time, mechanical design, the controlling parameter in mechanical design was strength. If you knew the strength of your materials, you could design a machine that would work. This little image right here is an artist's conception of the claw of Archimedes. And the claw of Archimedes was an ancient weapon designed to protect the seawall of the city-state of Syracuse in the Mediterranean Sea. It was used during the Second Punic War, about 200 BCE. The idea is that they could make machines of war or machines that would work if they could figure out how strong they needed to be. This image right here is from Leonardo da Vinci's notebooks. It's about 1600 years later after the Second Punic War there. But the idea is that this was one of the first tensile test machines, and it's recorded in Da Vinci's notebooks. Da Vinci was a military engineer. And in this case, he's trying to figure out how strong a piece of wire was. And he would drop pebbles or rocks into a basket, and when the wire broke, he would be able to record or measure or weigh how much those pebbles weighed, and he could figure out quantitatively how strong the wire was. In his case, he hypothesized that longer wires are weaker than shorter wires. We know today that longer wires have more defects, and wires with more defects are weaker than wires with less defects. But the idea is that Da Vinci was able to measure strength. And for thousands of years of human history, strength was the primary controlling parameter for designs. Things changed with the Industrial Revolution. In the Industrial Revolution, prior to the Industrial Revolution, most of power generation was primarily human or animal. There was some water power and there was some wind power, but generally it was human and animal. And the Industrial Revolution led to things like mechanized textile production, weaving and such. It also led to iron and coal production and pumps for the mines to get the water out of the mines. And things like steam. The only problem with the Industrial Revolution is the design of controlling parameters, or the controlling parameters used for design didn't keep up with these new designs that were showing up. This is an article from the London Times in 1842. there was a big party, a big fete in Versailles in France, in Paris. And there was, people went from the city of Paris out to the countryside where Versailles is located. They took trains out there because trains were new and open to the masses. They spent all day long on the grounds of Versailles and then came back home in the evening on the trains. One of the trains had 17 carriages with people in them, and it was pulled by the engines. And the problem happened when the train was about to enter into Paris again. And one of the problems was that the first engine, the axle, broke. So when the axle broke, the firebox, the coal-fired firebox, fell down onto the tracks. The other engines rode over it. The cars rode over it. And in those days, those cars were going pretty fast. They went maybe 25, 30, 40 kilometers an hour. And the idea is that because they were going so fast, you had to lock the doors to keep people from falling out. And those cars were nicely painted wooden cars, which when the firebox ran underneath them, burned. 6 of the cars burned, 3 of them totally. And as a result, there was a lot of people that died in that accident. And that caused, it was not the first time an axle broke of that first engine. It's not the first time an axle broke on a train. But the idea is it was the accident that caused the most loss of life up to that point for these new fancy trains that people were riding. That accident resulted in an international conference, and today we would call it the International Conference on Fatigue. But the idea is there was lots of theories as to why this axle failed, and lots of conjectures as to what was going on. Some of the theories were things like steam-assisted failure or percussion. Ultimately, the idea of the material getting tired or fatigued was the right answer. And a guy named a railroad engineer named Justus Wöhler, a German railroad engineer, was really the first guy to conduct fatigue experiments to try to quantify what was going on with these axles. And he took his experiments and he developed them and conducted them in various kinds of, changing various parameters for the rest of his life, essentially, for the next 18 years. So what Wöhler did is Wöhler rotated an axle. He hung a weight from it, simulating the car's weight, the train engine's weight, and he rotated that axle. The components or the elements of that axle, the upper element was in compression. If you have a weight hanging out like this picture in the 4-point bend in the lower left-hand corner. And the lower element is in tension. And as that axle rotates, the same element on that axle, the same surface unit, changes from tension to compression, tension to compression, tension to compression, similar to that graph on the right-hand side. The center line of the axle is essentially zero stress, and so he could hang that weight off there and change the weight and count how many rotations until he got failure, until the axle cracked and broke. This is extremely useful. I mean, this idea of figuring out how to quantify the damage based on a certain weight or a certain stress. And so we ended up calling this, engineers ended up calling this the stress life diagram, or the SN curve. N was the number of cycles to failure, and S was related to the weight or the stress that's alternating on this unit on the rotating axle. One of the things he discovered is that there is a point, for steels at least, at which below that, if you have a stress below that, the element or the component doesn't fail. That's not true for all materials. That is true for steels, some steels, and it's true at room temperature, but it's not true for all elements. But the idea, this was an extremely important document or an extremely important graph to be used for design purposes. If you knew the stress amplitude, you could design something that would achieve its ends. It would not fail during its design lifetime. This is an example of a more modern the idea is that this machine from R.R. Moore was very popular during the first half of the 1900s. Essentially with a motor that rotated the beam, or the axle in this case, with a counter on the end of it that counted the revolutions, and you could change the amount of weight that was sitting on that rotating beam. These are still around. You can find these in certain labs around the world. You can take that rotating beam idea and apply an axial load rather than a rotating load, rather than a bending load, and you have a much larger volume of material to explore then, because the volume of material in the rotating load is really just the surface elements, whereas in this axial situation, it's the entire gauge section of the specimen. And you can put an axial load on that specimen, and you can cycle it between positive and negative stresses, or you can use 2 positive stresses or 2 negative stresses or something else. The idea is that this axial loading is much more common in certain applications than the rotating beam is. And it's incorporated into the ASTM E466 standard, which is a load-controlled or a stress-controlled fatigue standard. Generally, that standard runs, initially it ran fully reversed. And currently, you can run it any kind of loading amplitude you want. We can talk about that a little bit later. But the idea is that designing this in a consistent manner was very important to design engineers. The SN curve can also be fit, and it can be fit by an idealized solution here. It's primarily a straight line in a log-log curve, and so there's an exponent, a fatigue strength exponent in Bathlin's equation. There's also a fatigue stress coefficient, which would indicate where that line intersects 0, or 1 as the case is, on a log-log curve. And once you record these coefficients, you can generally use them in any kind of design at any kind of stress amplitude that you need. And you can predict then the number of cycles to failure. Fatigue fracture surfaces are very different than tensile fractures. This is an indication, this is a failure here at MTS that it started at a surface, and you get a characteristic thumbnail. You get a fracture that radiates out from the initiation point. Sometimes you see beach marks on these fracture surfaces, and these beach marks are indications of where the load changed, or where the stress intensity changed, or the stress changed, really, the stress amplitude changed. In the lower right-hand curve, you can see a few beach marks of this broken part here. Just because we know how to design things doesn't mean we do them always the right way. And then there's other indications of fatigue. In this case, there's oxidation on the oldest part of the crack, and then the more rapid ductile fatigue is more silvery, and then the final fracture, that rough overload, that ductile failure, is on the right-hand side in this graph here. We have a much better understanding of fatigue and what's going on, but it's still a problem. In this case, this vehicle, this is a truck that failed outside of our factory on the highway. You can see what it's supposed to look like versus what it did after the crack grew through that part, did the overloading of the components. Let's talk about what affects these SN curves. So generally, things like material affect them. SN curve for steel is different than SN curve for aluminum. Geometry or notches or nooks and crannies affect how these SN curves work. The sharpness of the notch certainly affects it. The type of loading affects these curves. In other words, if you do axial loading versus bending loading versus loading history also affects these curves. If you do big loads followed by little loads, you get a different result than if you do little loads followed by a big load. And environment certainly affects it too. Temperature, corrosion, liquid, water, salt water, all those things change the way that these S-N curves behave. Things that increase the life include things like surface compression, like cold rolling or shot heating or nitriding or carburizing. If you put a compressive layer on the surface, the crack doesn't open nearly as quickly. Things that decrease the life, make these curves lower, are things like a higher mean tensile strength or a larger section, which would have more defects in it, or a rough surface finish, or a hard surface finish that, when it cracks, causes a notch, or maybe severe grinding of the surface. So these S-N curves move based upon these parameters. There are some things that don't really affect the S-N curve much. Frequency is one of those, at least frequency at room temperature. So you can run this test at a very high frequency or a relatively high frequency and get the same results as if you ran it at a lower frequency. When you start introducing things like time-dependent effects like creep or corrosion, all bets are off. I mean, that's going to change the amount of time you spent under that environment is going to change life. Another thing that does not affect the life much is the wave shape. You can run with sine waves, you can run with triangle waves, you can run with other kinds of wave shapes, and you should get the same life, generally. Generally, what we do is we run with sine waves because it minimizes the effects on the test machine. The sharp changes in direction are not as damaging to the test machine as they are with a sine wave. Sine waves are easier on the test machine. There are some things that do affect the S-N curve, and mean stress is probably one of those. I mean, there's lots of models out there to how to characterize mean stress, but generally, a higher mean stress results in a shorter life than a lower mean stress. A compressive mean stress is usually a longer life than a zero mean stress. So just to review this stuff, the idea is that cyclic stress is a controlling parameter for a lot of modern machines. And S-N curves can be used to study this high cycle fatigue. In the case of a low number of cycles to failure, there's too much plasticity to really be considered high cycle fatigue. So high cycle fatigue is really cyclic stresses that are elastic and usually result in a large number of cycles to failure. Constant amplitude at a cyclic stress is used in these tests, and it's usually stress controlled or load controlled on these machines. And the stresses are typically below yield. If they're significantly above yield, you have a lot of plastic deformation, which changes the way that micromechanisms work. Wave shape is not important, generally in HCF. Mean stress and frequency might be important, depends what other things are going on, what other environments being used. And most of those cycles are spent initiating failure. A small fraction of the number of cycles total to failure is used to grow a crack. Most of the cycles are used to initiate the crack or create the crack. And finally, failure location is weak spots in the material. In the case of these axial specimens, it's typically near the surface. Generally, it's near the surface because that's where the stress concentrations lie. So let's talk about something else. Da Vinci was, among other things, a military engineer. Unfortunately, wars generally create large technological changes, and World War II was no exception. In 1949, de Havilland Comet was the first commercial jet airplane. It was not a large jet airplane. It was designed to carry 20 to 40 passengers. It flew at twice the height of previous commercial airplanes, and it flew at twice the speed of previous commercial airplanes. Its first commercial flight was 1951. This was not Indiana Jones's DC-3 of the 1930s. This was something modern. During the first few years of its existence, the de Havilland Comet had 3 major crashes, 2 of them in 1954 and 1 of them in 1953. And all these crashes were due to explosive decompression. The the airplane blew up in the air and the parts rained down into the ocean, Mediterranean for one of them. The airplane had relatively large openings. You know, the windows were normal sized for the time, right? And it had relatively square openings. I mean, there was rounded corners, and these openings helped initiate cracks, and these cracks initiated at 1/10 the design cycles, so far earlier than than the models said they should initiate. The guys who made the Havilland Comet, the British engineers that made the Havilland Comet, needed to figure out what was going on. They took one of the airplanes, they put it on the tarmac, they filled it up with water, they pressurized and depressurized, pressurized and depressurized the fuselage, and they got a failure. They got an explosive decompression failure. And it was started at one of the corners of one of the openings. Essentially, that corner was going through a plastic strain change, plastically deforming. And that plastically deforming section of the material initiated cracks, and those cracks grew catastrophically. This ruined, I mean, these explosive decompressions ruined that company. But we are all much safer now because of that. We still have problems with decompression, with explosive decompression. This is from an Aloha Airlines flight in 1988. In Hawaii, the flights are relatively short. You know, 20 to 30 minutes is probably the longest flight you get between the islands. And in this case, it wasn't a design failure. It was more of a maintenance failure. There was poor maintenance done on a repair on this one. But the idea is that this flight landed, and everybody on board lived except for the flight attendant who was not buckled in at the time. But the idea is that explosive decompression happens rarely, but it still happens. But the idea of stress-controlled fatigue is not the only controlling parameter necessary for fatigue. There's also this idea of strain-controlled fatigue. We might want to identify how plastically deforming sections of a component might affect its fatigue life. And those are more strain-oriented than stress-oriented. So in the same idea that you can cycle things between stress levels, you can also cycle things between strain levels. Generally, these strain levels are plastic. And so generally, you plastically deform the specimen, make it longer, which means that you must squish it back to an initial size or a strain minimum value to cycle it again. Usually, these strain amplitudes result in compressive loading, even if the two strain amplitudes are positive. So that graph on the right could easily have a tension stress and a compressive stress, even though all the strains are tension. So let's just review what's going on so far. We have low cycle fatigue, which is strain oriented, and usually the strain is plastic. And more than, the total strain is what is being controlled, but some of that total strain is plastic, usually a significant chunk. Those stresses achieved during a low cycle fatigue test are usually above the yield stress, and it's a low number of cycles to failure in these low cycle fatigue tests. They're usually strain controlled. The strain is often, the strain wave shape is often triangular, because anybody who's run tensile tests knows that strain rate affects things like yield. It affects the way things might deform. So controlling the strain rate might be important in a low cycle fatigue test. It's not important in a high cycle fatigue test, in which things are cycling up and down on the elastic line. In low cycle fatigue, we might want to document the stress strain behavior. That becomes very important later on. And in low cycle fatigue, a smaller fraction of the life is used to nucleate a crack. The cracks initiate or nucleate fairly quickly in these specimens, and it takes a longer fraction of the life to grow that crack to failure, or a majority of life is spent growing that crack. In the case of HCF, most of the life is spent initiating that crack, and maybe the same number of cycles, but a small fraction of the life is spent growing that crack. HCF is usually load controlled. HCF has smaller strains and smaller loads. HCF is usually below yield stress. HCF usually has a high number of cycles to failure. And if we're trying to get the test done in a reasonable amount of time, that usually means you're running at a higher frequency. HCF is usually stress oriented and with a sine wave shape. And the information that's most important in an HCF test is probably the cycles to failure. The material response is elastic, and so it's more predictable. And so we don't really need to acquire things like stress strain hysteresis loops. Let's talk about stress strain hysteresis loops. The graph on the right-hand side is a typical plastic strain controlled LCF hysteresis loop. It shows a green total strain, and it shows a red plastic strain. The plastic strain is the width of that hysteresis loop. In most HCF tests, the plastic strain is 0. In most LCF tests, the plastic strain is not 0, is significant. Sometimes half of the entire total strain. In this case, the red region is half of the green region. The blue regions you can see down below that center line, that 0 line, are the elastic strains, or a way to measure elastic strain. Elastic strain is essentially what we're talking about when we're talking about stress-controlled testing. And so we might expect a Basquin-type equation for the plastic strain, but something else for the elastic strain, but something else for the plastic strain. Again, most of HCF tests are high frequency or higher frequency, so we can get the number of cycles on the specimen quickly, and it doesn't really affect the results significantly. Most of low cycle fatigue is lower frequency. Again, we can wait longer because the number of cycles is lower, and we want to usually control the strain rates. Remember the Basquin equation from above. In this case, we're talking about a Coffin-Manson equation, which is a way to predict the strain life cycles, the strain amplitude versus the number of cycles of failure. The idea is that this can be divided into 2 parts. One part is based on the elastic strain in the cycle, and one part is based on the plastic strain in the cycle. And these 2 parts are shown in the blue and the red down below. The elastic strain looks a lot like the Basquin equation, and the plastic strain amplitude is particular for the Coffin-Manson equation, or LCF. The idea is that if you know these exponents in this equation, you can probably predict what will happen in your test, and you can probably predict what will happen with your part. You can design your part appropriately, design your component appropriately. MTS got its start in fatigue. MTS got its start shortly after the Comet problems. MTS's first machines were designed in the 1960s, and this image right here is from the 1970s. But the initial MTS machines were not computer controlled. The initial machines did not have computer data acquisition or data storage on them. The initial machines used strip chart recorders and XY plotters and oscilloscopes and other kinds of manual paper measurements, essentially. Above this guy's shoulders, this technician's shoulders, you can see an XY plotter, and below his elbow, you can see the controller. And with that paper falling down on the floor below his knees there, that is the strip chart recorder used to record the peaks and the valleys or the wave shape as a function of time. This is a different image of an XY plotter, but the idea is that usually we're looking at stress and strain, or usually we're looking at load and displacement, which can be converted to stress and strain for constant cross-sectional specimens. This is what I grew up on. This is actually a very close image to my first MTS machine that I used. This one has a computer-controlled system. The computer is a PDP 1124 manufactured by Digital Equipment Corporation in Boston. This one had 8-inch floppies. You can see the floppies above the computer in the center of that picture. That console, they're on the right-hand side of that console. This one had a CRT. Some of the earliest machines had teletypes or other kind of typewriter kind of inputs. This one has a electronic display, cathode ray tube display. This one also is run, the fatigue on this system is run in a vacuum. That's a vacuum chamber between the crosshead and the base plate of that machine. ASTM B606 is the strain-controlled low-cycle fatigue standard used by ASTM. There is an equivalent, a similar kind of standard for ISO. And the idea is that because these standards, because these specimens usually go through zero, usually have tension and compressive loads on them, we need different kinds of gripping than we might use for a tension stress control test or for a tensile test in general. The loading needs to be able to go through zero without any slop or without any kind of mismeasurements. A modern system will have grips that allow that kind of loading. We'll have a power supply, a pump power supply. We'll have a frame that reacts to the forces and allows control. We'll have some transducers for measuring strain locally on the specimen rather than far away. And we'll have, a modern system will have a computer on it usually to take all those racks of electronics and turn them into something that fits under the desk. There's usually software then to control the test and to manage things. The software requires some kind of local strain measurement, and today that is primarily contact extensometry. But there's a lot of work in the video and laser extensometry world, and that work is going to overtake in the next few years the contact extensometry. These are examples in this page of different kinds of extensometry for that localized measurement. When you have aggressive environments, furnaces, hot or cold or corrosive, you need some other kind of extensometry to measure localized strain. And these are some examples of that. There's ceramic arms that go through the walls of the specimen that can withstand the heat that the specimen sees. Those ceramic arms touch the specimen and can measure strain locally on the specimen. Some of the grips that MTS sells, the most common grips are these hydraulic grips, which allow loading and tension and compression of the specimen without any kind of slop going through zero. But you need a different kind of grip if you're going to do things inside of aggressive environments. And so there's various grips that allow you to do that compression and tension through zero loading required by the strain control fatigue inside a furnace where the oil for these hydraulic grips can't go. The image on the right-hand side of the page there shows large grips that extend into the chamber, and that chamber can be hot or cold or can be salt fog or something else. The idea is that you need to put the environment you need to test in around your specimen, and you need to be able to grab it and measure its response locally. Another thing that's really important in modern test machines is the idea of alignment. You can, if you have any kind of bending strains on this specimen, that will screw up your data. That'll give you numbers that are not indicative of the true material properties of the specimen. One kind of misalignment is concentricity misalignment. That means that the centers of each end is not on top of each other. Another kind of misalignment is angularity misalignment, in which you're not loading it in a totally vertical manner. Most modern machines, fatigue machines, have some kind of tool to adjust the alignment to minimize the misalignment. And most of them use a strain gauge specimen to verify that misalignment has been adjusted out of those grips, that the grips are now concentric and with a parallel angularity to each other. And when we're talking about high temperature systems, we have a whole group of things that must work together in order to provide the right answer. Usually it's a grip, usually it's a fixture that loads the specimen but isn't hurt itself by the environment. Usually there's a furnace or some other kind of environmental chamber around the specimen. Usually there's some kind of localized strain measurement that allows you to get into the specimen, remove it, and put it back in the place later on. These are all parts that come with an MTS high temperature system. More examples of the high temperature kind of systems MTS can provide. Let's talk about what we're going to see next time in the second webinar of this series. We're going to talk a lot more about controls, about how do we get the right wave shape and how do we get the right control mode. We're going to talk a lot about perturbations or overloads or changes in loading, and we're going to talk about how we count cycles. It's not as simple as you might think. We're going to talk about data acquisition. We're going to talk about how we collect the right data and how much data we should store. If you want to store every single peak and valley, you will have the data you want, but you have a very big haystack and you have to find the needle inside that haystack. So generally, we don't store every single possible data point. We talk about test termination in the next webinar. We talk about how do you know the test is done? What does failure mean? Does failure mean two pieces? Does failure mean a change in stiffness? What does failure mean? And we talk about environment, both hot, cold, wet, corrosive, and the effects of environment on all these other pieces in a test. So our next webinar will talk about the details of the test, not just an overview like this one was. Now I think we're ready for questions.
Thank you, Eric. That was an informative webinar, and we're ready to answer some questions. Our first question, this is a bit broad, but maybe I'll let you decide how much detail to go in. What techniques are currently available or recommended for detecting crack initiation?
Oh, that's a hard one. So there's always a trade-off between sensitivity and so you can have false positives and false negatives, okay, in any kind of detection. And so if you make it sensitive enough to detect it when it actually first starts, you're probably going to get some false positives. You're probably going to get some things that think they're cracks, but they're not cracks. So you're really looking for a change from a baseline. And everybody who has done tensile tests know that yield can be defined as nonlinearity, but yield in ASTM E8 is defined as a 0.2% offset. So something far away, 0.2% strain is far away from nonlinearity. Same kind of thing has to happen in crack initiation or crack detection, in that you need to have a limit that says, I now know that this is a crack, which usually means that the crack is significant. It's not just starting. 1,000 years ago when I was in school, you could do things like replicas. You could put a piece of tape on the surface of the specimen and you could see if it showed a crack on that piece of tape underneath the microscope. That's a hard way to do it. It's a high-touch way of doing it. But it is probably one of the ways to find the very first indication of cracks. I'll just stop with that answer by itself.
All right, we've got lots of questions coming in. Coming in real fast, it's good. We've got, what's the best method for crack measurement in the case of high cycle fatigue? Can CTOD be used for that?
So a clip gauge, again, it's one of the ways to talk about failure, and we'll talk about this more next time, is a change in stiffness. And a CTOD gauge, or a crack tip, a gauge, right? A crack tip opening displacement gauge can be used to measure localized strain, and it can run at high frequencies. You know, the ones that MTS provides can be run at high frequencies. And you can use that with load signals to measure the stiffness of the specimen. It's related to modulus, obviously, and the idea is you can look for that stiffness to change, and the stiffness will change when the crack initiates. Usually, by the time you can see a change in stiffness, there's a significant crack, and so again, you're looking for a big enough change to call the crack there, but a small enough change to say it just started or it started not too long ago. And I think from experience, you're going to see that using a clip gauge and a stiffness change is going to be bigger than you really want. The crack is going to be bigger than you really want.
Great. Okay, here's another one. Can we do creep fatigue testing on an MTS frame?
Certainly. So the idea is creep fatigue. So fatigue is usually sustained load under temperature, okay? And creep fatigue is reversing that load periodically. The very first high cycle fatigue tests I ran in school were high cycle fatigue in a molten salt coated specimen at a temperature of 1300 degrees Fahrenheit. So 1300 degrees Fahrenheit is certainly creep oriented temperature. I wasn't doing sustained load, but I had a high mean stress on these specimens, which in a way is sustained load. It's not a constant load, but it's a constant mean load on these specimens. And what we were studying is keeping the maximum stress constant, how did changing the mean and the amplitude affect the cycles to failure and affect the life? And the life was a combination of cycles to failure and time under test. We wanted to keep the frequency relatively constant in this case. But the idea is that you can run those on MTS machines, and I certainly did. If you're going to have cycles that have a sustained hold time at the peak of days, that might be it's not a misuse, but that might be, an MTS machine might be overkill for that kind of creep fatigue test. But if the creep fatigue test is lots of cycles at a high mean stress at a high temperature, that's ideal for these MTS machines.
All right. Next, could you clarify this distinction between fatigue and fracture toughness testing?
Two different animals. So fatigue is response to a cyclic load or a cyclic strain or a cyclic stress. Fracture toughness is what energy is required, and energy is a loose term, to grow the crack catastrophically. And catastrophically is sort of a fuzzy term also. The idea is that you're using some parameter, some controlling parameter to identify as energy. Sometimes it's stress intensity, sometimes it's J integral, sometimes it's CTOD measurement. So fracture toughness is what kind of energy is required for catastrophic failure. And catastrophic failure can also be a fuzzy term. Like you said, it could be, when does the crack grow in a nonlinear manner? When does it grow very fast, like in a fraction of a second? When does it grow in a single cycle? Whereas fatigue is not about cracks. Fatigue, at least not initially, fatigue is about how does cyclic load cause cracks and cause failure, not how does the instantaneous value of a certain parameter result in failure.
All right, and here's another. How do different grips affect alignment? Example, thread versus cylindrical button heads.
It's a really good question. Threads are easy to manufacture. Everybody uses threads. Problem is, threads are easy to screw up too. So as a result, they can be difficult to align. One of the rules of alignment, one of the procedures for alignment is to rotate your specimen in the grips. And when you rotate the specimen in the grips, when you do with a threaded specimen, you're rotating it up and down into the grips in addition to rotating it in the grips, because the thread goes up a half turn if you're rotating the specimen 180 degrees. That's not true for a button head specimen or a smooth shank specimen or something like that. The MTS grips allow all these specimen shapes and sizes. There are different grips that are usable for round specimens versus rectangular specimens. The 647 model grips that I showed in that image are designed to work with both. The best alignable grips are usually the 646 grips, which are primarily oriented or optimized for round specimens. And they essentially start out pretty doggone close to aligned, and you can tweak them to be further aligned.
Okay, like I said, lots of questions. That's great. Keep them coming. This one we have is there a guide to design initial flaw and root radius for FCGR testing?
There is, but this isn't, I mean, for FCGR testing, for fatigue crack growth rate testing, yes, there's an ASTM standard for that, certainly, and there's an ASTM standard for how those notches should be created. That's outside of this webinar, right? But the idea is, I did my PhD thesis on fatigue crack growth testing, and so the idea is I know about this, right? But the details are outside of this webinar. The quick and dirty answer is ASTM E647 is the standard for fatigue crack growth testing at relatively slow rates, or reasonable rates for metals. And there's some detail in that standard. There are equivalent standards or similar standards in the ISO world, and there's a lot of national standards for fatigue crack growth rate testing. Some of those other industries go into more detail about the notch behavior. The simplest solution is EDM wire cutting these days, but you can, all this stuff is designed to work with the machine shops and guys who have machine tools that cut things, from a big blank of material.
All right, here's another. Can you mention how important the PID settings are for strain-controlled fatigue tests between different amplitudes, material, test temperatures, and changing material strength throughout a long fatigue test?
So PID settings, we're going to go into that more next time. Specifically, we're going to talk about PID to some extent next time. And the deal with PID settings is that proportional on a closed loop control system like an MTS system means that if there's an error between where it is now and where it's supposed to be now, how does it open the servo valve on the system to make the actuator move to reduce that error? If our command is a triangle wave and our feedback is not a triangle wave, meaning it's not where it's supposed to be, then we have to move the actuator by opening and closing the valve. Figuring out how much to open and close the valve is the duty of the PID settings, right? In the case of load control, the PID settings are relatively fixed based upon a stiffness. And the thing is that stiffness changes during these tests. As a crack initiates, the stiffness of the specimen changes. In load control, a big specimen will have a different stiffness than the same material small specimen, or a cracked specimen will have a different stiffness than an uncracked specimen. And as a result, the PID values may need to change during the test, or they may need to be compensated during the test. So in the beginning, we don't need to correct them much, but at the end, we need to correct them more. And so there's a variety of mechanisms for getting good PID settings to start with and compensated PID settings later on. We'll talk about that more next time.
Excellent. Okay, how should the inertia of test fixtures be accounted for during dynamic testing to ensure accurate measurement of the specimen's response?
Should be and can be are two different animals, right? But the idea is, so heavy grips, when they're moving up and down real fast, show a load on the load cell that doesn't really exist on the specimen. And you know, that's a problem, obviously, because you're not getting accurate load data from the load cell. That's usually not a problem at 1 hertz or 10 hertz or even 20 hertz, but we're starting to get into the neighborhood of 20 hertz. We're starting to think about it. The idea is you can compensate for acceleration, and one of the things that's easy to measure is acceleration on the load cell. And so if the load cell sees an acceleration, some of that acceleration is due to the mass hanging off the load cell, those grips and fixtures we're talking about here. And if you incorporate that acceleration into your load signal to correct your load signal, you can subtract off the bad stuff. You can subtract off the values that are due to acceleration and not due to actual load on the specimen.
Okay.
We call it Excel comp.
I think we have time for a couple more here. Are you able to use CT specimens per E399 for E1820JR testing?
Yes, but that's outside of this. That's all fracture toughness. But let's just talk quickly about one of those things, about part of that. So E1820 requires load line displacement, crack length, and essentially energy under the curve, but load displacement and crack length is what it requires. And the load line displacement can be fudged a little bit, okay? A specimen for E399, which is a K1C test, often measures the displacement not at the load line, but someplace else that's convenient, like the front face of the CT specimen. Using something like similar triangles, you can sort of estimate what the load line displacement is based on another measurement someplace else at not the load line. And so, yeah, you can use those CT specimens. It's not according to the standard exactly, but I think it's a small minor modification.
All right. Do you have any comments regarding ASTM E647K controlled fatigue? How is it similar or different to axial and bending fatigue?
It's sort of way different. So again, this is outside of this discussion, but the idea is that, so K controlled fatigue, K is the parameter representing stress intensity. Stress intensity is a function of load and crack length and geometry. And so the idea is that as the crack changes, you get a different value of K for exactly the same load amplitudes. So if you're doing a constant load amplitude test, the crack doesn't weld together, it only gets longer. And as the crack changes, the K values increase, delta K values increase, even though the delta load values are constant. A K controlled test usually tries to modify the load in order to make the K values, the max and min K values, what they're supposed to be. And if you want to do a constant delta K test, which is sort of a boring test because you only get one crack growth rate, you're shedding the load. You're lowering the load as the crack grows. More commonly, you do a K shed test in which the K starts at a high delta K and ends up later on at a low delta K in order to get a variety of DADN values. And that is way different than an HCF test, which is usually just a constant load amplitude test.
All right. When evaluating a hysteresis curve, would the area labeled in blue as plastic strain still be considered plastic strain in materials that may recover with time, such as plastics and textiles?
Oh, that's a really good question. And so sometimes we talk about inelastic strain, which is sort of a catch-all, versus plastic strain, which is really plastic deformation. So the stuff inside that loop was, in that instance, was really, it could have been plastic strain. But the idea is that there are times when we're doing a hold time at the peak load, or peak strain in this case, if it's a plastic strain control test. And the hold time at the peak strain often results in things that, and we're going to look into that more carefully and more fully in the next seminar. But the idea is partitioning the hysteresis loop into component parts is sometimes really important, and sometimes gives you great knowledge about what micromechanisms are actually happening in the material. And some of that recoverable information or recoverable stuff, the viscoelastic materials in general have recoverable information in them. And figuring out how to evaluate that hysteresis is important. We'll talk a little bit about that next time, but right now I'm limiting it primarily to metals.
All right. And we're running up against the top of the hour here, so I think we will cut off questions at this point. Thanks again for sharing your fatigue testing expertise, Dr. Schwarzkopf, and thank you to our audience for all their attention and insightful questions. If you want to hear more about fatigue testing of metals, please join us again in 2 weeks on August 26th for the second part of this series, where Dr. Schwarzkopf will share information about managing test variables to help ensure reliable data acquisition. Until then, keep testing. Thanks. Have a great day.